Today is sadly the last day of class. So we are going to end with what I promised you at the beginning of the class, that everything is the same. Well, at least with all the caveats that the system is engineered and that we can use constitutive laws and all the other restrictions that I have made on the way. But today we are going to see that electrical and chemical systems are sometimes the same, and because of the connection between mechanical and electrical systems, all three types of systems are sometimes the same. As an example, consider this RC circuit. Here we have many resistors that are connected together, and in between them, we have capacitors. And this circuit extends for a long ways in both directions. The circuit has lots of repeating elements, each of which has a capacitor and a resistor in a loop. All of the capacitors have capacitance C, and all of the resistors have resistance R. And I'm going to mark in Ci-1, Ci, and Ci+1 so that we know which capacitor we're talking about. The equation that we get for the charge on each capacitor is Qi dot is equal to 1 over RC times Qi plus 1 plus Qi minus 1 minus 2 Qi. Look at the right-hand side of this differential equation, and now look at the diffusion equation prior to taking the limit as dx goes to 0. We have d dt of c at some point xi is equal to d times c of xi plus 1 minus c of xi divided by dx minus c of xi minus c of xi minus 1, all divided by dx, and all of that divided by dx. This is the approximation of the second derivative of c with respect to x. Now that is equal to d times c of xi plus 1 plus c of xi minus 1 minus 2 times c of xi, all divided by dx squared. This means that the dynamics of the electrical system are approximately equal to the dynamics of the diffusion equation if dx is equal to 1. And d is equal to 1 over RC. Let's test this out and simulate the electrical system while plotting the solution to the diffusion equation on top of it. We can choose a total of n equals 100 capacitors, and r equals 0.1, and c equals 2. Moreover, we can choose the initial charge on every capacitor to be 0, except the one in the very middle, which we choose to have a positive initial charge of 1 coulomb. We plot the height of each state and watch it change over time, and we plot the solution to the diffusion equation on top of it. Amazingly, these two solutions are right on top of each other. Prior to the near universal use of computers for simulations, people used this relationship between the circuit and the diffusion equation to use a circuit as an analog simulation of how a chemical might diffuse in a fluid. What does this mean? It means that electrical systems can experience diffusion if there are enough electrical elements involved. Since electrical and mechanical systems are equivalent, it means that there is a mechanical system that is equivalent to the diffusion equation as well. In fact, one mechanical analog is a series of spinning masses with torsional damping between them, where we focus on the state v and how an initial velocity in the middle diffuses to velocities throughout the system. You might find it interesting that heat also diffuses in a mechanical body. For instance, if you touch a piece of metal with something hot, the metal will get hot, and the way it gets hot satisfies the diffusion equation. This is why sometimes the diffusion equation is called the heat equation. So even thermodynamic systems are sometimes the same as mechanical, electrical, and chemical systems. I don't know how you feel about this, but to me, this is a really beautiful and profound idea. But mechanical, electrical, and chemical systems are not always the same. We saw before that mechanical and electrical systems are sometimes the same if the components match up well. We see here that they are sometimes the same if there are lots of components and those components are very uniform. The resistance and capacitance of the circuit has to be the same everywhere for the circuit to be the same as the heat equation. Lastly, the relationship between mechanical, electrical, and chemical systems mean that we can use these physical analogies to understand how charge will diffuse through a circuit or how energy in a mechanical system will diffuse through its elements. The main thing I hope that you get out of this class is the sense that very different systems often behave very similarly. Of course, that doesn't mean that the title of the class is literal. Not everything is the same. But enough things are the same that understanding analogies between systems provides us with a way of connecting analytical reasoning with computation, and computation with our physical knowledge, and our physical knowledge back to the analytical reasoning. This ability to connect these different ideas and intuitions is part of what makes an engineer competent to make decisions, and I hope you find this class helpful in your future as engineers.